So let me introduce the next speaker. It's Yifan Wu of Northwestern, and she will talk about optimal scoring rules for multidimensional effort.
Yeah, thanks. So this is my joint work with Jason Hartline, Liren, Shan, Yingkai Li. So progress scoring rules, they are, you can see it in many areas. Like for example, in machine learning, they are used as loss functions, where the minimizer of the loss is the true distribution where the samples are generated. And since the proper scoring rule has this kind of property, in mechanism design, they are also used to elicit information. For example, in exams, if an instructor is using a proper scoring rule to grade the students, then the student should have the incentive to tell his true belief distribution about the answer of the questions. So in our previous work, we try to understand what kind of proper scoring rule are good under a binary effort model. So in that paper, we show some commonly used scoring rules can be very bad. For example, one common practice is the separate scoring rule. Like if you give out many questions and you score them separately, and the total score is the sum over the separate scoring, we show this kind of scoring rule can be really bad. So in this paper, we consider the multidimensional effort model, and we try to understand if the intuition from the previous paper also holds for the multidimensional effort model. So here's our motivation for the story. We are considering scoring rules for the classroom. So there is an instructor who wants to incentivize students to do assignments, and the student can learn by doing some assignments. But the problem is, doing each assignment induces a cost to the student. Only after paying the cost, the student can get a measurable signal. And the instructor has a value over the assignments that are learned by the student. So our goal is to design a scoring rule to optimally incentivize effort. So let's see if the students, they are not strategic and they are perfectly following the instructor's advice by doing the problem set. In this case, the principal faces a knapsack problem. She only wants to design the problem set from a ground set of n tasks, where each task has a cost to the student. And the principal wants to compensate the student by some score, but the principal is bounded by some score bound. Like in real life, you don't want to give a score that's higher than 100, and here we normalize it to be 1. And the principal is trying to maximize her value over the set, the problem set that is given to the student. And this is the knapsack problem. However, the students, they are strategic. First, they can choose a multidimensional effort. So if you are giving out a problem set, the student can choose any subset of the problem set, only pay the cost over the problem set, over the subset of the assignments they are choosing. And the second thing is the strategic agent, they have private learning outcome. So if they are not exerting effort, they don't know anything about the true answer on the problem. But if they are exerting effort, with some probability, they are learning the true answer, but with the rest of the probability, they still don't know anything. But even if they don't know anything, they can still lie about the learning outcome, like pretending, like guessing an answer and pretending to know it. And that's why we need a scoring rule. So the student, they are trying to maximize their expected utility, which is the expectation of score minus the total cost they are choosing over the set. And here's the principal's problem. The principal wants to design a proper scoring rule. So here's the definition of a proper scoring rule, which is an informal version. So we say a scoring rule is proper if it can incentivize the agent to tell the agent's true belief distribution. And also, the principal wants to design a problem set. So we say a proper scoring rule and a recommended problem set, they are incentive compatible if the agent does not have any incentive to deviate to do any other subset of the problem set. So here's the principal's problem. She wants to maximize her value by designing a scoring rule over the problem set and incentivize the student to do the problem set. So here are the results in our paper. We give a bi-criteria approximation. This is saying we can achieve the knapsack optimal without incentives by inflating the budget by a constant factor. And by fixing budget, we design a simple scoring rule that can achieve a constant approximation to the value. And under a different model where the agent can do sequential response, which means the agent can obtain a signal and decide whether he wants to do the next assignment. Under this model, we show the same scoring rule that can, under the static response model, also can achieve a constant approximation. And this is showing our scoring rule is robust. And if you are interested, look at our paper. Thanks.
Yeah, thanks a lot, Yifan.